that is not at all how I thought that would work. Oh, that is so cool. This weekend, I took apart this little pump I've been holding onto for 3 years, and what I found totally validated hanging onto it for so long. This is a windshield washer fluid pump from a 2011 Mini Cooper. It stopped working at some point, and while replacing it, something about this pump just caught my eye. Like any pump, it has an obvious inlet for fluid to enter and an outlet for fluid to exit. But the first sign of magic is that this pump has 2 outlets. 2 outlets alone wouldn't be too surprising. It could just have fluid come in and shoot out both sides. But that's not what happens with this pump. On this car, the front washer and the rear washer are activated independently. I double checked, and there's only one pump connected to the reservoir. So somehow this pump can choose which washer the fluid should go to. In this video, I'm going to demonstrate how this pump works, tear it down to show you all of its parts, and explain how all those small parts work together. I think you're really going to like this one. Before I destroy this magnificent thing for science, let's give it one last chance to fess up how it works. Using my benchtop power supply, the pump works as expected. Give it a few volts and fluid comes gushing out one of the outlets, but interestingly, nothing comes out the other. The whole thing is sealed, so it's not immediately obvious what it takes for the pump to just switch modes. The trick was remembering that this is a DC motor, so I have the option to reverse the polarity completely. When the motor reverses, the fluid comes out the other outlet, while still drawing from the same reservoir. Okay, we solved it, but something still isn't clear here. With a regular pump, reversing the motor would just draw air from your washers and push that air back into the reservoir. Not exactly useful. When this pump is reversed, it changes which direction the fluid flows and continues to draw the fluid from the reservoir. It really behaves like having 2 distinct pumps. Alright, I'm ready to get inside this thing. I see a DC motor, I see some contacts, I see a gasket to have the shaft pass through and not have fluid leak through. I see the impeller itself, I see the impeller cavity. It looks like this is the way the impeller spins inside the cavity. And then we have this valve body. Oh, that is not at all how I thought that would work. Oh, that is so cool. Now that I got it all apart, let me walk you through how I think this pump works. It is so neat. Let's talk about how the pump generates flow. When the impeller spins, it forces any fluid in its path in the direction tangent to rotation. The faster the impeller spins, the more water wants to escape. To convert all this useful pressure into flow, the pump just needs to keep the impeller spinning and have the outlet placed along the impeller casing. The flow will be best if the outlet is aligned in the path tangent to the impeller rotation. This pump also needs a consistent supply of water into the system, but we will get to that later. Reversing the direction of the impeller will create fluid pressure on the opposite side of the propeller fins. Fluid will have trouble escaping the old outlet since it is no longer in line with the path tangent to rotation of the impeller. But by adding a new outlet to the other side of the casing, we can get the same flow again, but this time only from the new outlet. I think this type of pump is called a centrifugal pump, maybe volute centrifugal pump. If you know the exact type, let me know below. So what about getting fluid into this casing in the first place? In the same way a plastic bottle collapses when you pour out of it too quickly, rapidly exiting fluid creates a suction to draw in new fluid to replace it. In this cross section, you can see a slightly larger cavity beneath the impeller, which connects to the reservoir spout. Even this funnel shape is critical for giving the fluid time to accelerate from the lower speeds in the stem to the high speeds seen by the impeller. So we have a pump that may pump in 2 directions, but there's still some problems. Without anything blocking off the outlet we aren't using, the pump may lose some of that pressure, or worse, suck in fluid from that side instead of the reservoir. So for this to work properly, the pump really needs to pretend that the other outlet doesn't exist. Cut it off from the rest of the system. How they solve this, in my opinion, is the most clever part of the pump's design. Let's take a look at the valve body. This part lives just beyond those impeller casing outlets we saw earlier. First thing I noticed was the outlets are connected. They both feed into the same shared volume of the valve body. Then they separate the volume with a thin, flexible rubber membrane. Let's call it the diaphragm. Okay, but how does this diaphragm help with cutting off one of the outlets we aren't using? Since one impeller casing is always positioned in the direction of flow, one outlet will always see more pressure than the other. This pressure differential results in a small force being applied to the diaphragm, shoving it to one side. To make use of that, we bring in the tubes coming off the valve body really close together so they're almost touching the diaphragm. Now when that force is applied to the diaphragm, it's enough to seal off the outlet on the lower pressure side. This seal prevents flow, essentially cutting it off from the system like it doesn't exist. When the motor is reversed, the pressure differential is reversed, so the diaphragm swings back and seals the other outlet. This prevents flow in that direction and enables flow in the opposite direction. I'm just going to take a moment to admire this thing. This is such a clever design. It uses such simple injection molded components and flexible materials to perform such a pretty complex task. It's the kind of solution that's so wild, it only makes sense on a product that's being designed for mass production. If I was tasked to design 100 pumps to do this job, I might have used 2 pumps or an actuator to switch which outlet I use. But when you're designing a pump that probably runs millions of units a year, reducing cost, parts, and complexity becomes so critical and really influences how you design the thing. Some cost savings that I can see just by looking at this. They obviously got away with one DC motor, which is probably the most expensive part of the whole thing. It's all injection molded plastic, which is going to drive the cost down as low as it can possibly go. There's almost no moving parts other than the ones that absolutely have to. We have the impeller and the one valve diaphragm that's moving. Everything else is just static. Even the way this white part clearly has like snap fit features and like a watertight seal everywhere. So there's no fasteners, it all just press fits together. I'm pretty sure this is an ultrasonic weld here. It looks totally homogeneous at the cross section. There's probably a big ultrasonic weld head. That's a process that uses ultrasonic vibration to weld plastics that are similar. It works super well, but it sounds awful. All right, I'm talking way too long about pumps. Next time you clean some bug guts from your windshield, I hope you think about this little pump and all the work that went into getting it to do what it does. Thank you for watching.